So the plan here for today, we're gonna be starting chapter 15. We're only gonna do a little bit of 15.1 today because the A-day classes only got 45 minutes or whatever on Thursday last week to do stuff. So rather than getting ahead and then having to catch up with them, I think we'll just slow down here. I know you're really upset. You're like, I only get a little bit of math today. Can we do more? Well, you can always read ahead. That's okay. Right? Or just go look at the Millennium Prize problems and see if you can figure out one of those. Win yourself $1 million if you can solve one. There's still a lot of open problems there. All right. So today we're going to be talking about, or starting, I should say, Chapter 15. Today we're just going to start section 15.1 about exponential and logistic functions. We're not actually going to get to the logistic part today. We're just going to start with the exponential part, but we see them at the end of the section, but we won't get that far today. As earlier specified, we're going to just, do a little bit of this because we're not off sequence with the A-day. So let's start by just defining what we mean by an exponential function. I guess before I do that, though, survey from you guys. Last year in your regular algebra class, you did not get to exponential and logarithms, correct? Okay. So my plan here, I'll be a little bit more careful and go a little slower than I would have than we did in the previous two chapters, where polynomials and rational functions are things that, to my understanding, you did do in your regular algebra class. And certainly if you're in the honors, you did those things as well. And you probably did exponential and logs also in the honors class. But all right. So we say that an exponential function is something that can be written in the form, I guess we'll write it f of x, in the form a times b to the x, where a is non-zero, and then b is greater than 0, and b is not equal to 1. So these different parts of our exponential function all get some names to them. So this coefficient at the front, this a value, we call the initial value. This b, we call the base of our exponential. And obviously the x is located in the exponent. We'll call that the exponent. And that's the key characteristic of an exponential function. When you see the variable in the exponent, that's what you're dealing with. So we have these extra restrictions here on the values for a and b. Let's talk about why those restrictions are in place. What would happen if a was 0? Would be f of x equals 0, right? That's just a constant function. That's not exponential, so that's not what we're looking for. And then we have that b can't be 1. What would happen if b was 1? Well, 1 to the x is just 1, so you just have left with f of x equals a, which again, constant function, not exponential. We don't want to include that. Why does b need to be positive, though? That's a little bit harder to see. So the b is the base for the exponential. Let's think about what would happen if that was just that number is like -2. Remember, x is a variable, so it could be any value we want, right? So x could be a number like 1/2. Why would -2 to the 1/2 be a problem? Well, remember, a 1/2 power is the same as a square root. And any like fraction that has an even denominator is an even root. Can we take the even root of negative values? No. What happens? You get an imaginary result, right? So this, if we allowed a negative base for this, you'd have a function with like infinitely many discontinuities. And boy, howdy, we do not want to go down that road, right? Like that is a big mess of a function. Everybody feel okay there? Okay. So every exponential function has a key feature that's a horizontal asymptote. And that horizontal asymptote is at y equals 0, but the end behaviors are either going to be, oops, let's do that. You're going to have one end going to 0 and the other going to either positive or negative infinity, or the opposite, where one end is going to positive and negative infinity, and the other end is going to 0.
And so all of them, all exponential functions have these end behaviors?
Yeah, one or the other, assuming they're written in this form, a times b to the x. Josh, what's up?
I always start that base back.
Sure. So just to kind of give you an idea of what we're looking at here picture-wise. So like if we're looking at these guys, you're looking at something that would look like this or that. And if we're talking about the green piece, you'd have something that looks like one of those two. Notice the one end is following that horizontal asymptote, and the other end is shooting off to either positive or negative infinity. So like all of your exponential function graphs will look kind of like one or the other. Or one of those four, I should say. There's really 4 pictures I drew there, right? You guys are all okay that I drew them all in one axis? So before we continue on, I want to identify a common mistake that I see students make. And if you make this mistake over and over again, it's going to spell doom for you. So let's say we have the exponential function 5 times 4 to the x. Is that equal to 20 to the x? Absolutely not. No, never. So recall that if I want to multiply two exponential numbers together, they either need to have the same base, in which case we can add their exponents, or they need to have the same exponent, in which case we can multiply the bases but keep the exponent the same. Right? Those are the two ways you can multiply exponential numbers. Either the bases stay the same, or they have the same base, in which case the base stays the same and you add the exponents, or the exponent is the same, in which case the exponent stays the same and you multiply the bases. Notice up here, what you have is like 5 to the first times 4 to the x. The bases are different, and the exponents are different. This is why you cannot multiply them together. Does everybody feel okay doing that? Again, common mistake I see students make. I want to take a moment and hit on this hard here and remind you of like what you can and can't do, because if this is a mistake you're going to be prone to make, we best get it corrected right now so that it doesn't become a big old mess before we get going too much further. All right. So you probably recognize both of these guys as properties of exponents that you would have studied in your Algebra 2 class, right? To help us just kind of get used to exponential functions and kind of remember some of these other properties of exponents that we haven't mentioned yet, but are things that are like really necessary that we have kind of remembered and memorized. Let's kind of do a little bit of an example here to just run through some of these other properties with some specific exampling along the way, just to kind of refresh our memories. So we're evaluating the function f of x equals negative 2 times 4 to the x. So if I'm doing f of 2, I'm just plugging 2 in for x. And now, according to order of operations, what operation happens first? The exponent. Very good. So 4 squared is 16. And then negative 2 times 16 is negative 32. Feel good there? No big deal. Then we'll do f of 0. So just like before, I'm going to plug 0 in for x. Remind me, what is 4 to the 0 going to be then? 1. Yeah. So recall, any number other than 0 to the 0 power is 1. 0 to the 0 is, well, for your purposes, we'll say it's undefined. It's actually worse than undefined. It's called indeterminate. There's 7 indeterminate forms. And indeterminate means simply what it says is like you can't even make it a value. Undefined typically means infinite. Like 1 over 0 is undefined. But 0 over 0, that's indeterminate. All right. But that's beyond the scope of what we're trying to do, indeterminate quantities. So let's do f of negative 3. So that's going to be negative 2 times 4 to the negative 3. What is 4 to the negative 3? What do I do for that? What's a negative exponent mean?
You have to change the sign every time you multiply the exponent.
Nope. It means we need to make a reciprocal. So 4 to the negative 3 is 1 over 4 to the positive 3. And 4 to the third is 64. And then I can just kind of reduce that guy down. Does everybody feel okay there? You remember that property from last year, I hope? Again, the point mostly for what we're doing here, get used to doing exponential functions, but to review these rules of exponents that at one point I'm sure we knew quite well, but in the interim, you know, time stuff fades. You know what's remarkable is you think back to 3,000-4,000 years ago, and ancient peoples would think nothing of memorizing the Iliad, like thousands of words of a poem. Think nothing of doing that. Now I can't remember our exponent properties from a year ago. Anyway, that's just time, I blame modern communication. You've never developed that muscle because you can just read it whenever you want it, because books aren't rare, or a phone is handy and it's Googleable or lookupable. You don't have to memorize it. All right, continuing on, this is f of 1/2. So what does 4 to the 1/2 mean? No, we mentioned it earlier. It's a root, right? So the denominator of the fraction tells you the index of the radical. So normally we don't bother to write the 2 there when we write a square root. It's like a number we accept is there, but we don't bother to write.
Will the numerator to that ever be different than 1?
It could be, yeah. In general, if it's still means kind of the same thing. You just, yeah, it becomes the exponent on the x, and you could attach it inside the radical or you could put it outside the radical. It doesn't really matter. Yes, sure. Does that feel good? But that's a great question. Yep. So all your unit fractions correspond to radicals. If it's a not unit fraction, then it's just, like it's a radical to some power, but that's fine. And then our next one. So we'll have that. F of negative 3 over 2. So now this is a lot of stuff to deal with right here, right? So my suggestion is we're going to do this kind of one step at a time. So the first thing I would want to deal with is the negative exponent. And then 4 to the 3 over 2 is really, I'm going to think about that as like 4 times 3 to the 1/2. Everybody's okay with that? I'm sorry, 4 to the 3 times 1/2. And that's multiplication, so it doesn't really matter the order that I do it in, right? Now, I prefer this way of thinking about it because I remember that the product in the exponent is like the same thing as the exponent of an exponent. And why would I like 4 to the 1/2 better than 4 to the 3rd to the 1/2? Yeah, because 4 to the 1/2 we already did, right? That's just 2. And again, the major property that we took advantage of there was like the power of a power property. Does that feel pretty good in jogging our memories as to like what these properties of exponents were and kind of how they work? That was the major point of doing those examples. Like, you could just type those things in your calculator and press enter and get the number to come out. That wasn't the point. The point was reviewing some of these algebraic properties because it'd been a minute since we'd seen them, right? And if we're going to deal with exponential functions, you're going to have exponential numbers rolling around all over the place that we want to make sure that we can manipulate appropriately. The next idea that we're going to talk about is going from points to a function. And we're going to see 2 types of examples of us doing that. So I'll start with the easier example first. So here's a table, and we're asked to find the function, the exponential function that passes through these points. Yeah, sure. Now, you probably remember, wait a second, Mr. Kulik. We did this way back in chapter 12, right? I just type the data table into my calculator and do the exponential regression on it, and it'll spit out a formula for me. You guys recall doing that? At least vaguely. That's true. We're also going to look at how to do this by hand in certain circumstances. So if I give you a full data table and ask you to do this by hand, I would only do that if one of the numbers if one of the x coordinates is 0. Okay? I will only ask you to do this if one of the x coordinates is 0. Actually, well, only ask you to do it by hand. So we're looking to write a function g of x equals a times b to the x. Now, what I have here is an xy, and I'll show you why having the x coordinate of 0 is an important point. Because when I plug that in, I have 3 equals a times b to the 0. What's b to the 0 though? 1. So what's that just tell me? A equals 3. Now I can choose any other point from my table, I'm going to choose the one that's the most convenient to work with. I love having exponent of 1. That's going to make life very easy. So now I'll do the same thing. But now I know A is 3. So if I just divide both sides by 3, I get that B is 5. And if I put those two together, I have g of x equals 3 times 5 to the x, which is obviously equal to 15 to the x, right? No! Reminder, is that equal? No. Don't do that. Makes math teachers cry. So it's just this. I'm going to try to scare you into remembering this once more, at least today. Don't be scared, though. I'm doing it for your own good, you know? I just need it to be memorable, so I have to do something. I left my clown costume at home.
So we should leave our answers like that.
Yeah.
If they can't,
If you can't combine them, that's all you can do, right? Everybody feel okay on that situation? That's pretty easy to deal with, right? You start with the 0x, and then any other point afterwards is fine, but do yourself a favor and pick, if 1 is an option, do x equals 1 as your next point, you know? If it's not, then take whatever looks the most convenient. Now, the other situation that I will ask you to be able to do by hand is where I give you just 2 points. So again, what we're looking for is to write a function h of x equals a times b to the x, right? Notice that neither of my x coordinates is 0. So when I plug in, say, the first point, I'd say 48 equals a times b to the negative 3, right? How many variables are still left in that equation? Still got 2, unfortunately, right? Can I solve an equation that has 2 different variables in it like that? Not with one equation. How many equations do I need to solve something like that? 2. So I will use my other point. I'll plug that one in. And that's going to make myself a system of 2 equations. Again, in your algebra class last year, you should have spent a fair amount of time, probably almost a whole chapter, studying different ways to solve systems of equations, right? Amongst the methods you probably studied were substitution, elimination, graphing, probably did some matrix methods. Now, this particular system that we've just written down is different than the systems you've seen, because most of the systems you saw were like 3a plus 7b plus 9c equals 10, right? The equations would have looked like that, where the variables were being added or subtracted from one another. Here, our variables are being multiplied. So we're still going to do elimination, but the elimination is going to look a little different, because instead of adding and subtracting the 2 equations, since my variables are being multiplied, I'm going to be dividing the 2 equations. So it doesn't matter whether I take equation A and divide it by equation B, or if I take equation B and divide it by equation A. But I can make my life a little bit simpler if I'm careful here. So I want to pick the equation that has the biggest exponent for b and make that the numerator of my division problem. So the one with the bigger exponent is equation B because -1 is greater than -3. So I'm going to do equation B divided by equation A. So the left-hand side is going to be 12 divided by 48. And the right-hand side is going to be A times B to the -1 divided by A times B to the -3. So far, so good. 12 over 48 reduces down to 1/4. The A's will cancel out. That's the elimination happening. And then how do I divide B to the -1 by B to the -3?
It's the formula.
So we had this property of exponents, that to divide two exponential numbers that have the same base, I can subtract their exponents. Remember, it's always numerator minus denominator. What does -1 minus a -3 give us? 2. Okay, so we'll then square root both sides. When I square root both sides of an equation, I get a plus or minus. How do I square root a fraction?
Both sides.
You mean top and bottom, right? Yeah, good. So again, so the square root of 1/4 is just going to be the square root of 1. That's 1. Over the square root of 4, that's 2. Is everybody okay here? Now, plus or minus here, guess what we can do? We're writing an exponential function, right? What are the requirements on our value for b for our exponential function? Has to be greater than 0. Guess what that allows us to do? Yeah, I can drop the plus or minus to just make it plus. So I have that. And now I'm going to plug that into either one of my equations, either equation A or equation B, to solve for the A. I'm going to plug that into equation B. Typically, I'm going to pick the one where the exponent's closer to 0. So -1 is closer to 0 than -3 is. Is everybody okay with what I did there? Okay. What is 1/2 to the -1 going to give me? Remember, what does an -1 exponent do? Makes a reciprocal. Perfect. Yes, so it just becomes 2 over 1, or just call it 2a. If I divide both sides by 2, I get a is 6. So if I take those together, I have h of x equals 6 times 1/2 to the x. Now, I want to point something out that I'm going to be picky about here. Whenever I have the b of my exponential function as a fraction, I need you to write the parentheses around it, because 1/2 to the x is not the same as 1 to the x over 2. Right? 1 to the x over 2 would just be like, that's the same thing as 1/2. the quantity 1 over x, or 1 over 2 to the x, is like 1 to the x over 2 to the x. Which would be that. So these two would be okay. You could use those interchangeably. But this one, not the same. Okay? So I'm always going to write them with any fractional. I'm going to put a parenthesis around it and the exponent on the outside of the parenthesis. That is something I will be picky about when grading your papers. Just wanting to point out some of these like finer details that I'm going to be picky about while we're talking about it, so that we've communicated it very clearly about what the expectation will be, so there's no surprises.
It's not just B, it's like if any of them are a fraction, you want them in parentheses.
Well, specifically the B. The B is the one that has to be there. In general, the A I don't really ever put in a parenthesis. The B, when in doubt, I'll just put the whole B in parentheses, whatever it is, whether it's a fraction or maybe if it's a radical or whatever, like that's fine. How are we doing so far? So far, so good? Okay, probably 15 more minutes. So there is a particular value of B that's a special value. So that special value of B is the number 2.71828, yada, yada, yada. This number is an irrational number. Do you remember what irrational means? Okay, so it means that it can't be written as a fraction. That means the decimal is never ending and there's no pattern to the digits, right? Like 1/3 is a never ending decimal, but there's a pattern. It just through, you know. So this number here, we're going to give a special name to. We're going to use the letter E to represent this number. We use the letter E as a way to honor the mathematician Leonard Euler, who did a lot of work in like algebra and algebraic geometry, who is credited with like this idea that we're about to kind of show you. And we'll show you kind of where we derive this number E from, where we get that number. But that'll come later in this chapter. We'll circle back to it when we talk about compound interest and stuff. It kind of falls out pretty naturally there. So the reason why this number is particularly valuable to us So the reason this becomes valuable to us is that we can rewrite any exponential function to have the base E. So instead of writing it as a times b to the x, we can write this as a times e to the kx. And what's nice about that is that if these two functions have the same base, it's much easier to compare them without having to look at the graph. So for example, if I wanted to compare y equals 2 times 3 to the x versus y equals 2 times 4 to the x, I would translate them both into a function like y equals 2 times e to the k. I put sub 1 x to indicate that those will be different numbers for k between the two. But now that they have the same base, it's much easier to compare like which one would be growing faster, slower, and that kind of thing. It allows us a means for comparison between the two functions without having to draw a graph. And we'll circle back to this idea again in future sections. All right. The last little bit I want to do is talk about the two major types of exponential functions. So we can classify all exponential functions as either growth or decay. So for an exponential growth function, we'd want something that's getting bigger as we move from left to right. So it would look either like the red or the green. So if I have written it this way, that would tell me that the A needs to be positive and the B has to be greater than 1. Or if it's the green graph, that's where the A is less than 0, but the B is between 0 and 1. And if it's the other form for our exponential equation, could be a greater than 0 and k greater than 0 for the red graph, or a less than 0 and k less than 0 for the green graph. And then a decay should be getting smaller as we move from left to right. So your decay graph will either look like the red or the green. If it's in the form we talked about at the start, would be a greater than 0 for the red graph, but the b value between 0 and 1. Or a less than 0 and b greater than 1 for the green graph. or if you're in the other form, that's a greater than 0, but k less than 0 for the red graph. And then a less than 0, k greater than 0 for the green graph. So those are just criteria for me to look at the formula for my exponential function and immediately decide whether it's growth or decay. Right? So all I really need to do is look at the a and the b value, or the a and the k value, depending on which form it's written in, and automatically I know which one what it's going to look like. Does everybody feel okay there? This is where we're going to stop. So at this point, you guys could be able to do like up to 8 on the homework. I'm going to assign all the way to 16. We'll finish the rest of this section next time to where you can do to 16. You probably can't get past 8 with what we've seen so far. Once you get to the story problems, you just stop for now. So that's kind of where we're at for today. Any questions on any of this so far? Feels okay? Felt.
That Euler guy just keeps popping up.
What's that?
That Euler guy, he just keeps popping up.
Yeah, man.
I like it.
E comes up all over the place in unexpected times and places.
I like it. I had it sort of in chemistry and astronomy and in here. I can't get away from this guy.
He's stalking your dreams. He's on the Hall of Fame here in the back of the classroom, too, if you want to read more about his biography.